Hello and welcome to everybody. Welcome to today's webinar. My name is Nick Lane. I'm the AAA Deputy CEO, I should say. I'm just doing a quick introduction to today's session for everyone and to welcome our speaker for today and introduce the topic. For today's webinar, if you have any technical assistance issues, please do phone Redback support on 1800 733 416. If you'd like to listen to the webinar through your phone rather than through your computer, you can dial in a number and passcode, which is listed in the chat box there on your screen. By way of introduction, today's webinar is on Regional Airport Pavements 101, and it will be presented by Dr. Greg White, who is Adjunct Professor, Associate Professor of Pavement Engineering at the University of Sunshine Coast. So Greg is a pavement engineer researcher at the USC, and as well as the Director of the Airport Pavement Engineering Specialists, an independent consultancy providing high-level and specialised advice to the airport industry. Previously, Greg worked as Technical Manager for airport projects at one of Australia's leading asphalt servicing and construction contractors, and as a principal airport and pavement engineer with a number of Australia's large design firms. Greg's interests extend to all aspects of airport pavement design, construction, management, evaluation and maintenance, particularly the incorporation of new and innovative technology and practice into real-life projects for the benefit of airport owners. As well as his PhD, Greg holds a Bachelor of Civil Engineering and 4 Master's degrees, all earned in the pavement engineering and airport pavement disciplines. So again, today's session is Regional Airport Pavements 101. This is now our second webinar in our series this year, which we're delivering to members, and it will focus on pavements, airport pavements for regional airports. Key topics that will be discussed are asphalt and bitumen for regional airports, sprayed ceiling for regional airports, pavement thickness and ACN, PCN for regional airports, runway frictions and skid resistance for regional airports, and pavement maintenance for those airports as well. If you do have any questions for Greg, please encourage you to use the chat box, which is located on the left-hand side of your screen, just to the right of the cogwheel. After typing out your question, hit enter to submit, and questions will be answered throughout the webinar. All webinars will be made available to members, so they'll be recorded, and we'll encourage you to provide any feedback on the webinar itself or any other additional topics that you'd like to see us deliver webinars on. But finally, before I do hand over to Greg, I'd just like to take the opportunity to thank Greg for his participation and his continued support. Very much appreciated, and it helps us to deliver interesting and informative presentations and events such as today's webinar. So without further ado, I'll hand over to Greg, and we'll begin the webinar. Thank you, Greg.
Thanks, Nick. I must admit, this is my first webinar as a participant or as a presenter, so I'm learning a bit as I go, but thank you kindly. We'll see how we go. I've probably got maybe a half an hour of material if I was just to sit here and present it, so that gives us hopefully plenty of time for questions, comments, thoughts that we can turn into a little bit of discussion along the way. As Nick said, this is USC is happy to support under the umbrella of the Airport Pavement Research Program, which was established in May this year, supported by the Department of Defence and some of the larger airports to allow the university to undertake practical and applied research that will deliver benefits back to the airport industry. As Nick said, this is the first in a series of pavement-focused webinars, specifically intended for the smaller, what I've been calling rural and remote airports. The content is loosely based around the Airport Practice Note 12, which was Airfield Pavement Essentials, which, as many would know, was released in conjunction with the Pavement Line Forum earlier in the year. Nick went through those other webinars that are planned to be undertaken as part of this series on pavement, so I won't re-dwell on those. Today's one, however, Airfield Pavements 101, for want of a better term, was really just to provide an overview and a bit of a background for those that are less familiar with what pavements do and why they do what they do, and sometimes why they don't do what we might like them to. So please ask your questions along the way. Some of them we'll answer as we go, some of them we'll leave to the end, but make sure we don't wrap up unless all of those have been at least discussed or resolved best we can. The scope of today is reasonably brief. So roads versus airfields, and why airport pavements are different from road pavements. Some of the basics around what a pavement does and how it does it. Structural and functional needs and the differences between those and how we cater for each of them. Quickly, loads and materials, and we'll talk about those more in the subsequent webinars in the series. And some life cycle stuff that is intended just to give a very broad understanding of maintenance requirements for different types of regional pavement surfaces and activities, maintenance activities. Roads versus airfields, I figured that this is about as good an explanation as one can get. So up the top we have lots and lots of relatively small vehicles that are all designed to move on roads, which means their centre of gravity is low to the ground and the wheels are spaced or located at the outside of the vehicle, making them relatively stable. In contrast, we have our aeroplane, which is large. There's usually not that many of them, certainly on the pavement at any one time, compared to cars. It's got a relatively high centre of gravity right up there with all the weight in the fuselage, rather than down there near the ground where the wheels are. And the wheels are located relatively close to the centre of the aircraft, which reduces its natural stability on the ground. That's all because aeroplanes are designed to fly, not to taxi, which means our pavements need to be a little bit different to make sure they can do so safely. There's a table from some work we did some time ago, just to summarise the differences between aircraft pavements and road pavements. And a couple of the important things are the load repetitions, maybe 100,000 versus more than 1 million in the road environment. The wheel loads, 25 tonnes. I probably need to update this now because some of the very large aircraft are more like 35 tonnes or getting close to it per wheel. And 20 to 25 would still be typical for the smaller airports up to 737 sized aircraft, compared to even a significant truck, which is more like 3 tonnes per wheel. In a similar way, the tyre pressures, they're also very high for airport pavements or for aircraft, up to 1.7 megapascals compared to about 0.8 in a typical truck. The other things that really drive the differences between airport and road pavements are the loss of aggregate. So on a road, if some loose stones come out of the surface and chip the car or chip your paint, that's very annoying. It's annoying for me. It's probably annoying for everybody. But it's a lot more annoying when that stone can be ingested into a jet engine, and in some severe cases can cause catastrophic failures and major events. So those things are the primary differences between airfield pavement requirements and road pavement requirements, and they're what drive a lot of the differences that we see in terms of the design, the engineering, and the materials that are specific to airport pavements. So moving along to pavement basics, again I figure a picture is better than a bunch of words. When you put a relatively significant aircraft onto typical natural soil, it doesn't work very well. And this is an example of that, where you've got some reasonably flat compacted ground and the aircraft causes ruts. Probably didn't have a great deal of friction. Clearly that plane was never meant to be on that grass, but it's a good demonstration of what happens if you try and put modern aircraft onto unprepared surfaces. So in general, all our pavements are designed to do is to protect the natural ground, which would otherwise be incapable of supporting aircraft loads and providing a safe surface for aircraft to travel on. Protects them from the loads. We can't do much about the loads. The aeroplane manufacturers will just reading PowerPoints available after the webinar. From my perspective, certainly can be. I'm sure there are some logistics to figuring out how that works, but I don't see why not. So the loads we can't do much about. The aircraft manufacturers make the planes to fly them. As airport designers, managers and owners, we just have to make our pavements acceptable for those aircraft. Our natural ground we also can't do a great deal about. Some airports are blessed, like Perth airports, built on nice naturally occurring clean sand, which makes a great material to build pavements on. Other airports are not so lucky, but there's little you can do about it. So with fixed loads and with fixed natural ground to protect, all we can do as airport designers, managers and owners is come up with a pavement to stick between those two things that makes sure that the planes stay safe and the natural ground is adequately protected, so that the pavement lasts for whatever a reasonable time period is, usually 20+ years. So in terms of designing that pavement and maintaining that pavement to perform adequately over that design life, we break the requirements into two sets: functional and structural. You could argue about some of these perhaps, but these are the ones that I came up with. From a functional perspective, we need our pavement to be fault-free so it doesn't damage the aircraft. We need it to have an adequate level of friction so that the aircraft can stop safely. It has to be adequately smooth so that we don't actually cause structural damage to the aircraft when it's moving at high speed, and appropriately shaped. And the shape is more about not holding water and not having high slopes that might encourage the plane to slide off to the side. We also require the pavement to have good visual definition, and that's usually achieved by line marking and airfield lighting, which are two things I hope not to talk too much about today. On the other hand, from a structural or for a strength perspective, the pavement needs to be strong enough for the aircraft to be carried in essentially a safe way, and for the pavement to fail in a safe way. So if you think about the picture that we had before, where the aircraft had skidded off the end of the runway, that grassed area had not failed in a safe way because it had created ruts. What we're looking for is something that fails slowly and predictably, so that we have time to react and we don't put aircraft in danger in the meantime. So if you think about these things in terms of MOS 139, all of those functional things are generally well detailed. There's lots of words that talk about FOD and friction and smoothness, the shape of the runway in terms of crossfalls and long falls. There are whole chapters in MOS, probably half the MOS dedicated to line marking and airfield lighting. On the other hand, that first dot point under the structural requirements to be strong enough for the aircraft, that's about all MOS actually says about the structural requirements, because CASA are focused on safety, and the structural element is less about safety and more about the cost of ownership and the cost of maintaining and rebuilding our pavements, as opposed to the safe operation of aircraft on them, which is why CASA doesn't say a great deal through the MOS about the structural requirements. And strong enough for the aircraft is almost 100% paraphrasing the MOS requirements from that perspective. It's also interesting to think that those functional requirements are mainly covered by specification details. So the asphalt, the grooving requirements, the construction tolerances that are required to be achieved by the construction contractor when he builds a pavement or a surface. Those things are generally covered by the details and the specification in the design documentation, whereas the structural requirements are to a large extent covered by the thickness design, which is just how thick and the pavement's going to be and what material it's going to comprise of. I'd never really thought about that until I put these slides together, but those two things almost perfectly categorise those functional and structural requirements as well. So moving along, this concentrates on flexible pavements because flexible pavements are what most of our regional airports have most of. This is sort of an illustration of how a pavement is intended to work. Down the bottom we have the subgrade or the natural material that we're trying to protect. Up here, of course, we have the wheel and the load that's going to be applied to it. We have a number of layers of material that, from a practical perspective, we consider to be continuous and uniform within each layer. And the idea is that we put the best materials at the top because they've got the most resistance to the loads, and we use those stiff materials to spread the loads and the stresses out wider and wider so that they're shared by a larger and larger area of the pavement until we get to a level of stress that's low enough that our poor old natural ground at the bottom can accommodate that level of stress repeatedly over our 10 or 20 or 30 year design expectation. So that's all we're really trying to achieve from a flexible pavement perspective, is to provide good materials that can spread the load out so that when we get to the bottom of the pavement, the natural ground is adequately protected. And this is, it's not the best picture in the world, but this is what we're trying to essentially stop from happening when we're doing that. We're trying to stop this depression here from actually occurring, because that depression, in theory at least, has been reflected all the way from down here at the bottom of the pavement through all the layers. In theory, the layers haven't failed. It's only the bottom of the pavement or the natural ground is where that depression has accumulated, and that's what we're trying to prevent. The relationships between how many times you can put a certain load on a certain pavement and how long it will last is all based on full-scale testing of real pavements conducted to a large extent in the 1950s and 60s by the US Army Corps of Engineers. And I quite often say there is no force equals mass times acceleration in pavement engineering. That's a fundamental principle of physics from which you can derive a whole bunch of other rules and laws of the universe. We wish we had one of those fundamental basic principles in pavement engineering, but we don't. Nearly all of our solutions are based on observing real pavements in the field or in test conditions, and then monitoring how many times we can load those until they're deemed to be failed, and then extrapolating that data to other real life circumstances or design scenarios. Not as much science in there as we might like to think sometimes. Moving on a bit to materials and loads. One of the important differences between roads and airports is that our airports don't have axle limits like we do on many roads. So most states in Australia have axle load limits. You can operate a truck to that limit, but you can't legally operate it at a higher axle limit than whatever's prescribed. which provides for essentially a cap on the strength that's required to be achieved by any road pavement in any particular state. It doesn't need to be stronger than that axle limit requires it to be. We don't have that kind of a system in the airport world, and that's largely a function of the fact that we have such a diverse range of pavement loadings. We've got everything from a small airport, say St George in Western Queensland, right up to the Sydneys and Melbournes and Brisbanes. And of course the plains are substantially different across that spectrum of airports, and therefore also the pavement strength requirements. However, we do have the ACN-PCN system, which I won't dwell on because I think we'll cover in a subsequent webinar in some detail. It's important to note though that the ACN-PCN system is really intended to cover, I've called them larger aircraft, but I really just mean not the smallest of aircraft. So I'm not talking larger as in 737s and bigger, I'm probably talking larger in small regional propeller turboprop aircraft, certainly Dash 8s and maybe even some of the smaller aircraft like the Saabs. But once you get down to that very small aircraft, let's say smaller than typically RPT aircraft, ACN-PCN is not intended to operate. And of course, we talked before, we don't have too much control over what our airlines purchase as their aircraft, and we don't have any control over what the aircraft manufacturers are developing. And so the aircraft is continually changing. This is quite different from the road environment where the loads are essentially capped at those state-based axle limits, and no matter whether you design a truck to be able to carry more than that or not, you just simply aren't legally allowed to load it any higher than that. It doesn't seem to work that way in the airport space because a load-limited aeroplane is very, or is not very cost-effective from an airline's perspective. So some of the things that, certainly from a regional or rural and remote airport perspective, are some of the changes in aircraft types that happen from time to time. Small aircraft to Dash 8s or Dash 8s, 100 and 200s up to Q400s, Q400s to any of the jet aircraft such as the Fokker 100 or the Boeing 737-800, which at the bigger end of the regional airport, spectrum, has become almost the workhorse alongside the A320 of Airbus, depending on which airline you have, I think, most of the time. So from loads, which we accept that we can't do a great deal to control, we can only limit locally by ACN-PCN to our materials. And really, this is a brief overview of pavement materials, and I just wanted to concentrate probably more on subgrades. And really, the intent is just to demonstrate the significant range in materials that we encounter. So in terms of the subgrade or that natural material, things can range from clays and silts, which are generally very poor, quite often found in low-lying areas. Western Queensland's black soils are a good example. Then in other areas we have gravels, and naturally occurring gravels still have sands and silts and clays in them, which is why you'll hear terms like a clay gravel or a sandy gravel as a natural material. They're generally better because the larger size particles give them some body, but they can vary substantially depending on the nature of the fine material that's in there. And sands, and we talked about sands a little bit before, and some airports are lucky, like Adelaide and Perth, they're substantially built on naturally occurring sands. Then you've got other airports like Brisbane and Cairns, where substantial thicknesses of sand have been dredged from the nearby seabeds to form effectively sand fields of substantial thickness. So whilst that's a lot of work, once they've been through that process, they end up with a very good material to build pavements on. we're not talking sand like at the beach, although it's the same material, but sand at the beach is very loose and moves around a lot. We're really talking about well-compacted, hydraulically placed and well-compacted sand, which is very dense and hard and makes a very good surface to build a pavement on, and it's free draining, so moisture content changes don't affect it greatly either. Good stuff once it's there. In terms of the granular materials, which we're usually using for our base and sub-base layers, so that's the bulk of the pavement, less the bituminous surface. Really, things fall into two categories. Quarried rock, which is usually hard rock that's been crushed or blasted, recovered and crushed in a quarry, well controlled, reasonably consistent and reliable. And then we have the natural gravels, which might be a deposit of natural gravel that can be used to build pavement layers. Those materials are usually uncrushed, and they have a lot more variability and they're a lot less controlled because they're naturally occurring. Bigger airports, and certainly closer to the pavement surface, will almost always have crushed quarried rock. As you get further away from the surface and you get further away from large aeroplane loads, the natural gravels become very advantageous because of the economics associated with them if you've got a good natural source around. The other key material in certainly our regional airport pavements are the bituminous materials, and I think this is the topic of the next webinar in this particular pavement focused series. So we won't go into them in great deal now, just to really categorise them in two ways. The first is sprayed seal, which is a spray of hot bitumen with the aggregate rolled in, very common in the more remote areas and the remote airports. And then asphalt, which is produced hot in a purpose-built production plant. It's actually a mixture of bitumen and aggregate, which is then placed as a uniform material or a semi-homogeneous material. A couple of pictures just to differentiate the two. When I met my wife, I made sure she knew the difference between spray seal, bitumen and asphalt, so I guess it's fair enough that we all understand those things. So you can see here the spray of bitumen and the spray seal, and then the stones are put on top and essentially pushed in by the construction rollers. As a result, the aircraft wheels actually run on top of the stones, and you can see in the picture there below that these are all stones that don't have a bitumen coating on the top. The bitumen's all underneath, and it's actually just holding the stones down onto the pavement surface. And this contrasts with asphalt, where you can see here a substantial thickness of material that has actually been produced in a machine by mixing the large stones with the smaller stones with the very small stones, and the bitumen and some other materials all together into a sort of a homogeneous mass, which is then placed on the ground and rolled, which produces this nice surface that you can see down in the bottom left-hand corner, which we then commonly cut some nice grooves in, because that asphalt surface will have substantially less natural surface texture than the sprayed seal surface will in the previous picture or the previous slide. The last thing we wanted to do was just talk a little bit about life cycles, and I recently presented a little bit of stuff on this at the Pavement and Lighting Forum, and I misled a couple of people inadvertently by with some of the rules of thumb that I presented. So please take these as rules of thumb. Typical answers, I've put some fairly wide ranges on them, but please don't go and take them as gospel without some actual project-specific advice, because they're not necessarily always going to apply in all circumstances. But from a regional airport flexible pavement perspective, you might expect to seal a few cracks every 2 to 5 years. You might expect to be doing some line marking every 2 to 5 years. If you've got a sprayed sealed surface, you might be expecting to reseal that surface every 8 to 10 years. And if you've got an asphalt overlay and you keep all your toes and fingers crossed, you might hope to get 10 to 15 years out of that surface. There are certainly examples where some of those numbers have been substantially exceeded. I know that I was involved in a project recently where a 33-year-old asphalt surface was resurfaced, and to explain to them why 33 years out of their next surface was probably not a likely expectation. But there have also been a number of examples where significant failures have occurred well within that 10-year period, and airports have had to resurface their runways within 4 and 5 years. From a structural perspective, most of our airport pavements are designed to last 15 to 20 years, and in practice we routinely get 20 to 30. And if you're resurfacing with asphalt, on a regular basis, then that almost becomes an infinite life from a structural perspective, because the overlay resets the structural life each time you do it by filling all those depressions back up. And the big disclaimer is that all of those things are highly dependent on your aircraft loading and your environment and your maintenance regimes. And of course, if you change planes, for example, from a small Dash 8 to a Q400 or to any of the regional jets we talked about before, such as the F100 or a 737, then all bets are off and you've really got to start over. And so in summary, I haven't seen too many questions pop up, so we're either going to finish quite early or we'll have a flood of questions imminently. But in summary, the pavements are really there to protect the natural soils, which is a structural requirement, but they're also there to provide a safe environment for the aircraft to operate on, which is a functional requirement. Our pavement designs are largely still based on empirical performance, which means pavement performance as it's been observed in the field over many years and either extrapolated or interpolated to the specific design scenario at hand. Our loads vary greatly, especially between regional airports and let's call them very, very remote or rural airports. And our materials vary probably even more. In terms of maintenance, all airports should be expecting to do minor maintenance every couple of years and significant maintenance every 8 to 15 or something like that. That brings me essentially to the end. A couple of questions flowing in, which is good. What have we got? Jared's asked, do I concur with the PCN overload advice in CAS's advisory circular, specifically 8 movements per week at 15% with no visual obvious degradation? That's a very difficult question. I think there are different organisations that have provided different advice about overloads. I think in general it's all relatively conservative, and 8 movements per week of 15% would probably be at the 8 movements per week of 15% would probably be at the upper end of what you might call the range of advice different people provide. I know that I assume it's still in there, the Department of Defence's Aircraft Pavement Strength Evaluation Manual, and perhaps even their pavement maintenance manual had some traditionally accepted by the FAC in its day overload advice. I also know that the FAA in the States are currently working on overload full strength testing specifically for overloads, and they'll provide some advice at the end of that process, but that's still some time away. I think if you're considering overload on a regular basis, so you're saying, well, I want a new aeroplane to come into my airport and it's got an overload of, say, 10% or 15%, and I'm going to have it coming every week for the foreseeable future, I think you really need to revisit your pavement strength and your PCN almost from first principles, rather than relying on some overload advice, which would be intended to be occasional or one-off. That's a good question. How is the study of asphalt rejuvenation treatments going? So that's a reference to the trials that were done at Sunshine Coast Airport. They were put down in February, I think, from memory, this year. The two students that have been working on that have got their last round of testing scheduled middle of August, and will certainly, the intention is to present the findings of that at either a pavement and lighting forum or perhaps a pavement workshop, which is being considered in conjunction with the OPSWAP in May next year. So I don't know if that's been officially announced yet. Hopefully I haven't let the cat out of the bag, Nick, but that's been the discussion anyway, and so we'll present those outcomes at one of those or the other. But no, the trial itself looks good. I haven't been out there for a little while, so it's probably about time to go and have another look. Comments regarding materials specified and locally available in remote locations. I think the gist of that is around, we have if you like, one generic specification to a large extent that's adopted by most of the designers in this country, and of course there are some certain circumstances where the availability of materials to meet those specifications is either extremely limited or highly cost prohibitive. And so I think it becomes a bit horses for courses in those circumstances where if you've got a serious airport with a serious pavement that's going to be seriously stressed, you want the best materials you can have, but at the same time it's got to make sense from a cost perspective. There are certainly many occasions where the materials are specified like it's Brisbane Airport, but they're going to, for example, perhaps Dubbo Airport or I don't know, there's been a few lately. So I think there needs to be certainly some common sense in those remote locations about materials, and that common sense should most definitely reflect the budget available, and in particular the aircraft and the type and location of pavement that's being either constructed or maintained. There's clearly a big difference between shoulders for a small aircraft and main taxiway pavement for a larger aircraft. Questions are coming now. When you mention minor maintenance, more specifically, what do you mean? I guess when I say minor maintenance, I mean line marking, crack sealing. I might even throw periodic friction testing in there. Maybe the odd patch from time to time, depending on the circumstances. And then I would call things like, let's say, full area rejuvenations or enrichment treatments. I might call that something that's a bit more significant in terms of maintenance, and certainly asphalt overlays would fall into the significant or major maintenance categories. Probably about it. Minor maintenance, crack sealing, line marking, and the odd patch repair if and when required. the most common complications in different locations and how much this can add or complicate build times and costs. So that's another good question. Probably the thing that varies the most and can cause the biggest impact is the airport's operations. So if you're at a small airport where they can close the runway because they don't have flights, say from Thursday, let's say Friday, Saturday, Sunday, Monday, you can do 4 days of work during the day. You could consider double shifting the crews. You could get a heck of a lot of work done, and some airports have had great success delivering their projects like that. But if you're at another airport where there's an RPT flight every day at midday, you can't close anything for 4 days, and you're going to be forced to schedule your works around those aircraft. And they're the things that change substantially. And they're the things that make, let's call them traditional designs, not work when you need expedient solutions. And they're also the kind of circumstances that really drive some of your design decisions early on. Because the two have to be in harmony, and I've been quite critical in the past where the two aren't in harmony, where you have a perfectly sound design, but you've got a set of operational circumstances that are just so far away from allowing that design to be physically achieved that you end up defeating yourself. Thoughts around computer modelling softwares available for airfield design? That's a good question. I think we had a great presentation and discussion at the Pavement and Lighting Forum earlier in the year about pavement design software, and I guess I observe a trend in designers wanting something that has an authoritative basis that they can essentially utilise to justify their design solution, and that's perfectly understandable. And that, to a large extent, means that we're adopting FAA solutions and the FAA software far field. As was presented at that conference and a bit of work done more recently, those softwares are adding substantial thicknesses to pavements. And my view is that unless we are conscious of that and we're willing to pay and happy to pay for that, if you like, peace of mind, then in my view it's hard to justify adding additional thickness and therefore additional costs to our new pavements when our traditionally designed pavements using APSDS or some of the other softwares that don't have that, if you like, international endorsement or authority to them have performed perfectly well for many, many years. I think it's something that we should try and resolve. I don't know how we'll go about resolving it though. My personal solutions are based generally on FAA's COMFA software in design mode, not in ACN calculation mode, but in that design mode, COMFA softwares and APSDS when the traffic spectrum is complicated, and just because it handles multiple aeroplanes much better than COMFA does, which requires you to effectively manually add the effects of the different aeroplanes together, which is a bit of a painful thing to do. Should I miss one? Will the pavement research program involve repeat of the AAA survey of members years ago on experiences with their pavements? In fact, I think it was about April this year, Simon Burke from the AAA actually put a survey out essentially as a repeat of that process. I still haven't seen the responses, and I don't know how many responses were received, but that actually did happen either late last year or earlier this year. So that's certainly something for the Pavement Working Group to follow up. with Simon. I would like to provide my maintenance manager with some basic manoeuvring area training. What would you suggest as an introduction? I'm going to ask Salomon if you can maybe restate your question again about manoeuvring area. I don't know if you mean from a pavement perspective or from a driving around the airfield perspective, the latter of which I wouldn't comment on. But maybe if you can just clarify that, we can come back to that one. Rodney asks, with asphalt pavement, is there a recommended aggregate size for a 40mm pavement? So I think he's asking if you want to put 40mm of asphalt on your surface, total thickness, what the size of the stone should be. That's a fair question too. So the general rule of thumb is that the minimum asphalt thickness should be between about 2.5 and 4 times the size of the stone. So 40mm is right on that awkward limit between a 10mm stone and a 14mm stone. Not too many airports have used 10mm size asphalt in recent years. Most have transitioned to 14mm, particularly on runways, for the increased stability and improved groove performance if you're grooving your surface. The other thing I think is worth noting is that if you're going to do an overlay and you've got a minimum thickness of 40mm, then you're probably typically going to need an average thickness of around 50 to 55, because your pavement won't be perfectly shaped. So you're going to have to fix some shape somewhere. And I've seen a number of airports recently where they've assumed a typical thickness, say 50 or 60mm, or perhaps even 40, although 40 is a bit thin, especially if you're going to groove it, so it depends on where you're going to do that. A minimum thickness, times that by the area to get a volume, times that by a typical rate, set a budget, which is all great until they then subsequently go and get a design and they realise that they need 50% more asphalt or 20% more asphalt than they budgeted for, because they hadn't made an allowance for shape correction. So my advice would be to very early on get some specialist advice about the typical volume of asphalt you'll expect to need to achieve what you want to do from a pavement performance perspective, but also to allow for that shape correction when you do your overlay. What is the relationship between aircraft movements and the frequency of major pavement maintenance if the pavement isn't overloaded? I think in general there would be a very, very low correlation between those two things. Most of our pavement is largely untrafficked most of the time, and so our asphalt resurfacing cycles, unless they're triggered by something unusual like rutting or either rutting or groove closure, then it's going to be environmental degradation of the surface that drives resurfacing frequency, and that's not going to be largely impacted by aircraft operations, although you'll get a bit more scuffing where the aircraft regularly touch down. In fact, my old colleague Ross Monteith always used to say that the best bit of the spray sealed surfaces were where the aircraft had been regularly trafficking, because it kept the bitumen moving and alive and stopped it from just sitting dormant and going rigid. So in some cases, the frequency of traffic can actually be beneficial to resurface or surfacing life. Lichen growth on a runway successfully. That sounds like an environmental question to me. I'm just going to skip over that one, Samantha, sorry. No. the short answer. Next question is, do CASA define how surface friction texture should be measured? I'm aware of the requirements but unsure as to how they have adopted accepted test procedure to measure texture or friction. Yes, that's a very good point. The current MOS says you must achieve 1 millimetre surface texture and/or the ICAO recommended levels of friction. The challenge with doing that, and it won't change in the new MOS 139 as far as I'm aware, but the challenge is that the international guidance was written as guidance. It was written as advice in a general sense, and because it was advice and in a general sense, it didn't have to be prescriptively explained, and they didn't have to provide a test method, and they didn't have to provide protocols for actually how to do it. That was never the intention of ICAO or the FAA when they put together that friction and surface texture guidance. It was really advisory for information. When in Australia, through the MOS 139, we made those things mandatory, we made something mandatory that was always intended to be general in its nature, which means that we, if we choose to make it mandatory, really need to then define how to measure it, what to measure it with, when to, how often to measure it, and a whole raft of other things, and be darn sure that we're doing that in a repeatable way. The current MOS doesn't even make an attempt to do that. The draft of the new MOS makes some attempt, but I think, personally, I think there's a long way to go in terms of making that something that is reasonably repeatable and taught reasonably repeatable. The majority of airport pavements with asphalt surfaces are not grooved. Surface friction is achieved by playing with the mixture design and materials. What's your opinion, do you think? Yes, okay. And then Luca goes on to say that he or she, sorry, I'm not sure who Luca is, was referring to European airports, and that's certainly the case. In continental Europe, the UK aside, many of their airports are not grooved. They use a number of specific asphalt mixtures like stone mastic asphalt, open graded friction coarse, or something French that I can't really pronounce, but it's, the acronym is BBA. They use all of those things to achieve the 1 millimetre surface texture in their surface. There's something important to remember in that, is that if you have a normal, traditional, dense graded Australian airport asphalt surface, it will only achieve about 0.4 to 0.6 texture when it's new, if you don't groove it. So unless you're going to change the whole basis of your surface asphalt mix, then you need to still be grooving. Even the AC 20 mixes, which were tried by the Department of Defence in the 80s and 90s, still didn't achieve the 1 millimetre surface texture. My view is that of all of those mixes that Europe has used, stone mastic asphalt has the most promise. Of China's 35 biggest airports, something like 34 of them have got stone mastic asphalt ungrooved on their runways, and they report good results. So I think that's something that our university research program should definitely be investigating. The ability for us to adapt, not blindly adopt, but adapt stone mastic asphalt for, in particular, regional airports in Australia, so that they can avoid grooving, and the risks associated with group closure. Yes, Nick's just sent me a comment that says we're going to have to wrap it up there because we're just about out of time. Well, the last question I will just, sorry Nick, Ravi's question is about bitumen types for asphalt, especially in remote areas. And my advice is, you know, make contact separately because I'm happy to talk about that stuff all day. But the next webinar is bitumen and asphalt for regional airports, and so we'll talk about that in some detail there. But fair to say, the hardest part of flexible airport pavements at the moment is bitumen and asphalt. I think that's a fair comment. So I don't know how to stop it, Nick.
That's fine. Thanks, Greg. Some great questions from everybody there, and certainly I think, Greg, as you alluded to, if anyone does have any questions that they'd like to pose to Greg, certainly send them via the AAA, or Greg, if you're comfortable, you know, you've got your details there up on your slide there now. If you want to email you directly with some questions, I suggest you know, please do. But thank you very much, Greg. It was a fantastic presentation and some great questions there from everybody. We really do appreciate both, Greg, your participation and University of Sunshine Coast's support as well, and also to everybody that did dial in today. We hope that you enjoyed, got some good learning out of today's presentation, and as Greg's already alluded, there will be some further webinars in the series, so keep an eye out for those in Airport Alert. Just before everybody does sign off, we do have a short survey there on the right-hand side of the screen, so if you do have the opportunity to, please do give some feedback there on today's session. That really does help us moving forward with our webinar series. So, just a final plug for the AAA here. The AAA National Conference in November, we have extended the early bird rate, early bird close-off for registrations there. So that's now been extended through to Friday the 11th of August. So you've got essentially a couple more weeks there to access that better rate there. So I encourage you to pop on over to the AAA's National Conference website and have a look at the program, which is looking like a really hot ticket this year. So please do go over and have a look, and there's an opportunity to register via that website as well. So thank you again to everybody, and I hope everybody has a fantastic rest of the day, and just keep an eye out in Airport Alert for details of further webinars. Thanks everybody, and thank you again, Greg.